Okay, good morning, everybody. Hopefully we'll get some slides up here on solutions and concentration. I am heaing the rumblings of how Newton is ruining your life right now.
Yep.
Yeah, we need to overthrow it.
Need to overthrow Newton. So what I will think about doing here tomorrow and over the weekend is lightening up on it. I'm not going to back off of it, but I will lighten up on it. I mentioned earlier there on the energy module, which I forget what, I think it's module 10, I will open up the homeworks, but they won't have any points associated with them. They'll be there for you to learn a couple of the concepts and maybe no quizzes. And I'll hand out a paper homework. It'd be fairly simple and straightforward. Module 10, what I expect you to learn out of that is mostly the vocabulary, and there's one equation. You were introduced to that equation in 1105 lab, those of you that had it, the calorimetry equation. So we'll lighten up on module 10. The two most important modules right now are this one, not that one isn't important. I want you to be aware of the things that are in that talk about energy, but we're not going to do a deep dive into them. So the two most important modules right now are this, solutions, concentration. This is chapter 6, but it's module 9, is it? Yeah. Module 9. And then module 11 is acids and bases. So I will look very carefully at what homework assignments I require in module 11 and quizzes. There might be one quiz on module 10, maybe one quiz. So I'll lighten up on it a little bit as we finish the semester, but we won't abandon it. We'll try to work with it a little bit here. All right, so in this, I mentioned molarity. The three main things you need to get out of module 9 is molarity, and you're going to need to kind of relate to that as a capital M. When you see a capital M, we're talking about molarity. Don't get this mixed up with this or moles or any other thing. The capital M is molarity. We're going to talk about weight, volume, percent, and we're going to talk about colligative properties. Okay, that's a big word, but this talks about freezing point, depression, boiling point, elevation, and osmotic pressure. And these relate to solutions and the concentration. So we'll get there. But so for right now, I'm going to soldier through a number of slides and just mention some things. And again, you can go into Newton and get more detail. And I want to get over to this and then talk about this a little bit more detail. By the way, to wake you up, I got to share this with you. Now, my Northwest Vista College students gave me this yesterday. Okay, I gotta prelude that with this. They gave me this yesterday. That we were turning in homework. Someone brought this up, and it looked like one of my homework assignments. Somebody's homework? How am I supposed to grade that? And then they said, oh, it works. They said, pull on its tail. Is that cool?
That's pretty cool.
So this morning, to show you that I was awake, I set up my camera and videotaped this for my grandkids. That's just a good morning. I said, I want you to get ready for college. This is what you got to be ready for. College. My students gave me this yesterday. Okay. Happened right here at NBC. And it wasn't, the student who made it didn't give it to me. Some other student from the other side of the room comes up and hands it to me, and I said, Dustin, what is this? He said, Brianna made this. I said, oh, Brianna, why didn't you give me this? I don't know. It's a wild class. All right, solutions. So let's work through some of these relatively quickly. Just to get solutions, we talk about a solute and a solvent. All right, now you're used to thinking about this with regards to water. Water is the solvent for a lot of things. All right, your blood system uses water. It's the solvent. It's the medium. You make a cup of coffee. That water is the solvent, and dissolved in there is some coffee or some sugar or whatever. So we've got a solvent. It's the larger quantity substance in the solution, and a solute. The solute is what you're dissolving into it. Now, to just broaden your mind here, solutions can be all kinds of things. You're used to liquid solutions like salt in water or sugar in water. It's an aqueous or liquid solution with water as a solvent. But air, the air we're breathing, you can think of it as a solution of oxygen dissolved in nitrogen. Air is an 80% nitrogen, it's 20% oxygen. It is a homogeneous solution. Solids. You could take copper and zinc. You melt them. You melt the copper, you melt the zinc. This would be at very high temperatures. And you pour them together and mix them together, and you get a brass. All right? And it's a solid solution. All right? So just they are homogeneous, which means they're uniform composition throughout. Solutions are. They are homogeneous. A Valero gas truck pulls up. I was getting gas yesterday, and right in front of me they were unloading more gas in that gas station. So there was a tanker full of gasoline. It's a solution of a lot of different compounds. Octane, pentane, hexane, just all different kinds of organic molecules of different molecular weights there, but it's a homogeneous mixture. If you would take a little sample out of that tanker and analyze it, it would match the composition of the whole tanker. That's the beauty of a homogeneous solution. That's the beauty of that, is that you can sample it anywhere and it represents the entire solution. So true solutions are homogeneous with uniform properties. Aqueous solutions, they're water-based. We won't worry too much about that. You can take a liter of water and a liter of alcohol, and you don't get 2 liters of solution. They will dissolve into each other and pack a little bit differently, and you get actually a little bit less than 2 liters. But we won't dwell on that one. All right, this is an important concept, and lean on Newton here to understand this, because I do think there's a Newton assignment on electrolyte and non-electrolyte solutions. All right, basically, if you take an ionic compound like sodium chloride and dissolve it in water, what happens if you take this sodium chloride, and remember, it's crystals, it's a big array of sodium and chloride ions, and you put it in the water, what you will have floating around in the water are sodium ions, all surrounded by water, and chloride ions surrounded by water molecules. It will dissociate into the ions that make it up. If you take sugar, if you take a chunk of sugar, a cube of sugar, here we have C6H12O6, and you put it in water, what actually is floating around in the water are molecules. They're still surrounded by water, but they are individual molecules of glucose floating around in the water. Okay, well, so what's the big difference here? These have no charge on them. They're neutral molecules. These are charged particles. They're ions. We've got ions floating around in there. And so what's the big difference there? This conducts electricity. And this doesn't. This is a non-conductor. Does not conduct electricity. If you put electrodes down in here and ran a wire through here and had a little battery, and a light bulb up in here, you could actually, the electricity that solution would complete the circuit. This solution would complete the circuit, and you'd have a flow of electricity, and the light bulb would come on. If you did that with a sugar solution, no circuit. If you did the same thing over here, and you ran a wire, had a battery, had a light bulb, the light bulb wouldn't come on. Why? Because you would not complete this circuit across here through the solution. Doesn't conduct electricity, conducts electricity. One thing you have heard is that water conducts electricity, which isn't really very accurate. Water with ions dissolved in it conducts electricity. All right, so just pure water itself is not a real good conductor of electricity. But you don't usually have pure water. Even if you're at a lake, certainly if you're at the ocean, there's a lot of salt in the ocean, it conducts electricity. So you have to kind of qualify that. Water with ions in it conducts electricity. And the more ions, the more of a conductor it is. So do appreciate the difference between an electrolyte solution, non-electrolyte. And how do you get these? Well, almost any ionic material you dissolve in water is going to produce an electrolytic solution. Sodium chloride, potassium chloride, magnesium chloride, magnesium nitrate, whatever they are. If it is an ionic compound and it will dissolve in water, then it's going to produce an electrolytic solution. But if you just dissolve molecules, and I don't know a whole lot of examples of these, it'd be any sugar is a good example. It dissolves good in water, but it is not an electrolyte. It's not an ionic compound. All right, solubility, and I'm saying some of these things pretty fast, but I want to move through to molarity. Just know that, solubility, we're talking about how much of something is able to dissolve in the water. If only a very little bit of it dissolves in water, like calcium carbonate is not very soluble in water. So we would say, well, it's really not very soluble. Is it totally insoluble? No. You can get 150 parts per million of calcium carbonate in water. But you can't get 20 grams of it to dissolve in 100 milliliters of water. That would be a lot of calcium chloride. But you can salt, table salt. So table salt is very soluble in water. And there are things that affect it. These are the two to pay attention to. The polarity And water, again, is a polar solvent.
Do you have these slides somewhere?
Not yet.
Okay, which one?
Sorry, I don't. I didn't post these yet. I didn't post the Newton slides. These are my normal solution slides. I'll get them posted. Yeah, that's true. I forgot about that. So water is a polar solvent, and it will dissolve polar substances. Polar, and that includes ionic substances. So alcohol is a polar molecule. The alcohol that's in alcoholic beverages is polar. It's not ionic, but it is polar. And sodium chloride is even more polar because it'll break apart into distinct ions. And polar solvents dissolve polar substances, molecules or ionic substances. The rule of thumb here is just keep this in mind. Like dissolves like. Like dissolves like. If it is a polar solvent, it will dissolve polar substances. If it is a non-polar solvent, like gasoline, gasoline will dissolve oil into it. Oil and gasoline will mix. Why? They're both non-polar. So they will mix. So that's what I mean by like dissolves like. If it is a non-polar solvent, then it's going to dissolve non-polar substances. And then the other one to keep in mind here is temperature. If you increase temperature, you increase solubility. So increasing temperature usually increases solubility. Here's an example. Again, sodium chloride. At room temperature, 20 degrees centigrade, so that's room temperature, roughly. Depends on what room you're in, but that's common temperature. Like here, this is 21 degrees centigrade here right now. You can dissolve 28 grams of sodium chloride in 100 milliliters of water. If you put 30 grams in at room temperature, you put 30 grams in, 2 grams will be sitting at the bottom of the container. You'll see salt at the bottom of the container. And you might say, I don't think the salt's soluble in water. Oh yes, it is. It's very soluble in water. It just is not infinitely soluble. Okay? So just because you see some that didn't go into solution doesn't mean the material isn't soluble. That container is very salty, saturated. Once it reaches its saturation point, nothing more will go in there. But if you heat that water up to the boiling point of water, you could actually get 58 grams of sodium chloride dissolved in it. So we say sodium chloride is soluble. It has a high solubility in water. Now we don't say that about silver chloride. It's still, you'd say, well, it's still a silver ion and a chloride ion. It's still an ionic substance. Yes, but silver chloride is not very soluble in water. 0.09 grams in 100 milliliters of water. Now compare that number to the 28 up there. Let's just round that off to a tenth. So we're comparing, we can get 28 grams of sodium chloride in 100 milliliters of water at room temperature. We can only get about a tenth of a gram of silver chloride. All right? So I would say silver chloride is insoluble in water. That doesn't mean that if you had some silver chloride around, there isn't some of it in the water. There is a little bit of it in there, but we don't say it's soluble. That's not good enough to really give solubility. Okay, I'm going to just wing by this. So if you had 28 grams of sodium chloride in 100 milliliters of water, we would say that solution is saturated. And if you want to make a saturated solution, you just keep putting it in there until you start seeing some of the material sitting at the bottom of the container. Then you know it's saturated. Because it has dissolved everything it can dissolve, and there's still some around there, so it could, if there was the capacity for it, more would go into solution. That's saturated. You can supersaturate a solution. You can, if you were to take that sodium chloride right there, boil it, get 58 grams of salt in there, it's saturated now at 100 degrees centigrade, and take it and sit it at room temperature and let it cool down. For a while there, you would see no crystals forming. It's coming down. It's 90 degrees. 90 degrees, it shouldn't be able to hold 58 grams of salt, but it's in there. 80, 70, 60. Until that very first crystal forms, it's going to be super saturated. It's actually got more stuff in there than natural or normal. And then at some point in time, when a crystal forms, it will start crystallizing out a solution. So that's what we mean by saturated, supersaturated. You can go and YouTube this if you want. This is a supersaturated solution of sodium acetate. And then let's see, I don't know if I have let's see if this will play. Can I get that to play? No. They take this supersaturated solution of sodium acetate, you don't see any crystals in there, and they pour it on a crystal of sodium acetate and they form a column. Right, it doesn't pour out on the table. It just builds up into a big column of sodium acetate. So there it is, supersaturated. Or if you were to take that crystal and drop a crystal into the supersaturated solution, it will go from that to that in a few seconds. It just bam, all this sodium acetate comes out of solution. Okay. Concentration. This is where I want to get to. And the calculations. Molarity, this is the most common expression unit for concentration in the laboratory, in the chemical laboratory. Molarity, moles per liter. Weight volume percent is the most common in the clinical environment, in the hospital. Saline solution is 0.9%. That means it's 0.9 weight volume percent. 0.9 grams of saline per 100 milliliters of solution. We won't, I'll just mention this one, we won't, and Newton might do some of those calculations. Weight percent would be the case like brass. If you are making an alloy, then you would express the alloy in terms of the weight of the one metal versus the weight of the other metal. Weight percent. That would be that. So we're not going to, we in the laboratory, we're mostly dealing with aqueous solutions where we're dissolving a solid in water. So we want to know the weight of the solid, we want to know the volume of the solution. So we go with molarity, moles per liter. Okay, so what is moles per liter? or what is molarity? It's moles of solute per liter of solution. Moles of solute per liter of solution. All right, so here is a liter. These flasks right there, here, they are called volumetric flasks. Volumetric flasks. 1,000 milliliters. 1,000 milliliters is a liter, right? It's 1,000 milliliters per liter. There is only one mark on this flask, right up there. And if you see that, like that is actually etched on there. This mark is not drawn on there, it's actually etched into the glass. So they've etched a line right on there. They're saying that is a liter. So they make these flasks, and then I guess they calibrate them, figure out where a liter comes up to, and they etch it on there. And this is exactly a liter. So if I made a solution in here up to there, I'd have a liter of solution. I'd have my 1 liter of solution. Now let's say I want to make, a 1 molar sodium chloride solution, and I want to make 1 liter of it. So I would get a liter volumetric flask. And what do I need to put in here? Well, water, but before the water, how much salt? 1 mole. 1 molar sodium chloride is going to be 1 mole of sodium chloride per 1 liter of solution. So what is the molarity of a solution containing 1 mole of sodium chloride in 1 liter of solution? Okay, what I'm doing, I'm just taking what I'm given and I'm plugging it into this equation. Molarity, moles per liter. Now, if I wanted to make this, I would have to get some sodium chloride. And now, can I go across the hall here and stand in front of balance and it's going to read out in moles? No, it's going to read out in grams. So how much of this would be needed to make that solution? I see Joel looking at the periodic table. That's good. That's good. It's good reflex. Sodium chloride. 1 sodium. And it is 22.99 grams per mole. 1 chloride, it's 35.45 grams per mole. So sodium chloride is 58.44 grams per mole. So if I had, sorry about that.
We can see you on the screen.
This is too much fun. It's way too much fun. So, let's work with that. So we have 58. So if I took 58.45 grams of sodium chloride and put it in here, and it is 1 mole per 58.44 grams, and it is in 1 liter of solution, okay, so I'm just saying that's how we would make it. We would go and get sodium chloride, put 58.44 grams of it in this flask, and then we would get some DI water. Now I'm not going to add a liter of water to this. I'm going to add water to make it a liter of solution. Okay, I want to make that distinction. It's not 1 mole of sodium chloride per liter of water. It's 1 mole of sodium chloride per liter of the final solution. So how much water do I add? I don't know, but it's probably not a liter. The sodium chloride is down in here, 58 grams of it, 58.44 grams of it. You add up the water, you put the water in here until you get the meniscus right here, mix that around, and you would have a 1 molar sodium chloride solution. You with me? Now, let's say, boy, you know, I only need 80 milliliters of this. I only need 80 milliliters. I'm going to make a liter and throw 900 milliliters away? Well, let's make a 100 milliliter. Let's make 100 milliliters of a 1 molar sodium chloride solution. 100 milliliters is 1/10 of a liter. It's 1/10 of a liter. I'm making 1 molar sodium chloride. I only want to make 1/10 of a liter. So how many moles of sodium chloride? How many moles of sodium chloride would I put in 1/10 of a liter to make a 1 molar? 1/10 of a mole. If I had 1/10 of a mole of sodium chloride in 1/10 of a liter of solution, right? 0.1 divided by 0.1, any number divided by itself is 1. That would be 1 molar. All right, so that introduces you to one thing, that when you talk about molarity, even though it's moles per liter, you don't have to have a liter of it to have something that's at that concentration. So we do have, because this situation arises quite often, where you say, I don't want a liter of this stuff. I don't want to just be throwing away all these chemicals when I only need 80 or 90 milliliters of this stuff. So I've got a 100 milliliter. See, does that look like it's about 1/10 of that? All right, 10 of these fit in here. So I got 100 milliliters. Oh, tell me, what is 1/10 of a mole of sodium chloride? I'm going to go across the hall here. Matter of fact, I already did go across the hall here to get 1/10 of a mole of sodium chloride. How much did I get?
5.84 grams.
Yeah, it's 58.44 grams per mole times 1/10 of a mole. All right? So stick with me. We're doing some of these calculations. So if I had 5.844 grams of sodium chloride, and it is 1 mole per 58.44 grams, and I had that in a 1/10 of a liter container, volumetric flask, I did this calculation right here in the numerator, so molarity equals moles per liter. So that's what I'm doing here. In the numerator, I'm figuring out how many moles of this stuff do I have here. In the denominator, I'm figuring out what is the volume of the solution. 5.844 divided by 58.44. Yes? Is that right? We're following me? I mean, we're just kind of doing what we did right there, but I'm just showing you how it all set up. And also, when you see, I'm writing here 1 molar what? 1 molar sodium chloride. It is not a liter, it's a 1/10. So, I went before class started, I've got 5.844 grams of sodium chloride right here. So here's how I would make this. I would get this sodium chloride down in here. Now I'll show you a little bit of lab technique. You see some sodium chloride left in there? See some little dusting there? So to do a quantitative transfer of that sodium chloride, I wash my sodium chloride down into there. And I'm doing all this before I add any of my solvent. And then I add my solvent, which is water. And I'm stirring it, trying to get that salt to dissolve in there, trying not to squirt my computer.
Laundry, that's why our chemicals, like, they never weigh out right.
Now this is just sodium chloride. Whenever I go over there and grab chemicals, Jeanette always gets a little nervous because she's concerned about what I'm bringing over here in the classroom. And I'm bringing salt. Oh, I don't want to finish hot off. Okay, see, I'm not there yet. Let's dry this off. All right, so now I want to finish this off really nicely. Should have a little pipette. That's pretty good. The meniscus is just a tad below. I don't want to get a lot. That looks pretty good. That looked pretty good. The meniscus. What can she say? She's going to say no. Egypt, is that okay? Okay, there we go. So there is a 1/10 molar sodium chloride solution. Can't tell that much from water, can you? Looks like water. Now it's very bad lab technique to taste your chemicals, so I'm not going to taste it. But I do want you to see concentration. So let's do a few more calculations here, and I have another chemical here, and you can see the concentration. So let's say you do this calculation. We're gonna work with copper sulfate. it actually ends up being copper sulfate pentahydrate. But let's say we're working with copper sulfate. And I want to make a 10th molar copper sulfate solution. Make 100 milliliters, or 0.100 liters of this. All right, so you kind of go through the calculations. Let's start right here. Molarity equals moles per liter. So it's going to be moles of copper sulfate per liter of solution. What do we get as a molar mass? Okay, did everybody get that? 159.62 grams per mole. So how many moles of copper sulfate do you need to put in this flask to make a 1 molar?
Or did I calculate it wrong?
Yeah, you got the right number.
Oh.
You're talking about molar mass?
Yeah.
No, you need to take that 159.62 times a tenth.
Oh, okay. I was dividing by this.
Yeah, well, you take that. Yeah, you've divided by tenths, but that's a mole.
Oh, okay.
We only need a tenth of a mole.
Oh, okay.
All right. So what do you have to put in the flask? A tenth of a mole, right? So we need a tenth of a mole of copper sulfate in the flask. So what is a tenth of a mole? It's 1 mole. No, it's 159.62 grams per mole. So what we need here is 15.96 grams of copper sulfate in a tenth of a liter solution. That's going to be my tenth of a mole. Yeah, 15.96 grams of copper sulfate. It's 1 mole. It's 1 mole per 159.62 grams. All right, so this expression right here, that weight of copper sulfate, it's 159.62 grams per mole. That is going to be 1/10 of a mole of copper sulfate in 1/10 of a liter of solution. So here we go. Here's our copper sulfate. Now copper sulfate is blue. I'm putting it in 1/10. I'm going to try. This is a lot of stuff here. Let's see if I can do it by water. Whoa. Now you know why Jeanette gets nervous.
Yes, I have a question.
Yeah?
So, how do you get 0.1 M? Because if we divide 0.1 of the mole over 0.1 liters, it comes up to 1.1.
Yeah. Well, that's what we do want to make. We're making 1 molar.
Oh, okay.
We are making. Make 0.1 molar. Make 1 molar. I'm sorry. Yeah, we want to make 1 molar, just like we made the 1 molar sodium chloride. Yeah, the 0.1 would have been a lot less. This ends up being 1 molar copper sulfate. I'm trying to make, I'm sorry there, I want to make the same thing. We made 1 molar sodium chloride. We made 100 milliliters of it. So I'm doing the same thing with the copper sulfate. We lost a little bit here. So we're going to try to ignore that. That wasn't a very quantitative transfer. But here's our copper sulfate. You see, and we can see the concentration here. Boy, I don't know. I wonder if I exceeded its solubility. I probably did. Copper sulfate may not be this soluble.
So when we get a decimal for the answer, is there any rounding in this? Or is it going to just be 0.9? No, well, we divide by 0.1, you didn't get 0.9.
Well, don't you have exactly 0.1 in the numerator and the denominator? No?
If you get, well, we did the 15.96 divided by 159.62, and then get that answer and divide by 0.1. You get 0.998.
Uh-oh, I've reached the solubility limit of the copper sulfate. I can't get it all to go into solution. So I can't make a 1 molar copper sulfate solution. I mean, I do have 1/10 of a mole of copper sulfate in here, but it's not in solution. So, but you can see, it does make the point. Some things you can see that they are there in solution. Copper is one of them. Copper plus 2 ion is blue. The copper plus 2 ion, whether it's copper sulfate, copper nitrate, copper chloride, it's blue, and you can actually see the solution. And I don't know, I was going to make another one here of lower concentration. Let's see if we can get all this in solution. This is half the amount of that copper sulfate. I was going to try to show the difference between these two solutions. Let's see if we can get all this to dissolve. difference. Well, look how dark that is. Yeah, if all of that will go into solution, it'll be fine. It's almost there. This one still has quite a bit there. Look how dark that, look how blue that is.
Would you call that saturated?
Yeah, that one is saturated. I don't know if this one's going to end up saturated. We'll see. If any of that stays around, it'll be saturated, but it may all go into solution. And I'll just fill that up. There. I'll fill this one up. All right. Can you see any difference in color? Yeah, maybe a little bit. This one is still a little saturated. I mean, it's not all dissolved. Well, I should have worked. But this is 1 molar copper sulfate. This is half molar copper sulfate. This is half molar. So you can make them different concentrations just by, so instead of putting 15.96 grams in here, there's only about 7.5 grams in here. Now, we're dealing with cute this morning. Pharmaceutical companies, now they're making solutions of stuff that is maybe $1,000 a gram. Okay, they got a new drug, very expensive. They don't even want to make 100 milliliters of it. There's times when they only want to make 10 milliliters of it. So there's a 10 milliliter volumetric flask. So I could make a 1 molar copper sulfate solution with a very little bit of copper sulfate.
Do it.
Do it?
Yeah, I want to see it.
There's my copper sulfate, but I don't have a balance. Okay, so just weigh out. Well, let's do it mathematically. If I got 10 milliliters, and it's 1 liter per 1,000 milliliters, that's 1/100th of a liter. So I would only need 100th of a mole of copper sulfate per 100th of a liter of solution. Molarity equals moles per liter. Remember, on all these problems I have you solve, I say go to the equation. Molarity is moles per liter. So if I had a 100th of a mole of copper sulfate in 100th of a liter solution, it would be 1 molar copper sulfate. So what is 100th of a mole of copper sulfate? It's 159.62 grams per mole. So it'd be 1.596 grams of copper sulfate in this little flask, 10 milliliter flask, and I would have a 1 molar copper sulfate solution. Well, you can see concentration, something like copper sulfate. The more concentrated the copper sulfate will get, the deeper blue it will be. Just faint, a faint blue color. Like if I were to take, I do have one more of these flasks. So if I want to dilute this one, this is 1 molar copper sulfate. I want to dilute it down to 10th molar. I could take 10 milliliters of this. Yeah, oh, not bad. I could take 10 milliliters of this and put it in a 100 milliliter flask. Get it all in there and fill that flask up. And now what I'm doing, I'm diluting the copper sulfate. Notice as I dilute it, I'm not changing the amount of copper sulfate in here. I'm not changing the amount. The moles of copper sulfate is in there, but I am spreading it out in a lot more water. I'm running out of water. Oh, that's salt there. Just so you could see, well, this is my day. No, I'll get a little bit more in there. It's close. All right? There's the solution I took it from, but I added a lot more water. I diluted it. And you can see I diluted it. It's a lower concentration here. It's 1/10 the concentration is here. It's 1 molar, 10th molar. So you can see concentration in some things like copper sulfate, nickel, chloride, they have color. So that's dilution. I can take a solution of known concentration and I can actually dilute it down to another concentration by adding more water to it. All right, let's just look through this and cover molarity well. So this is what I've been talking about. Mark, can you turn these off for this front one just for a second? So there's your volumetric flask. 58.44 grams of sodium chloride in there, and then fill it up with water. Calculate the molarity of a 150 milliliter solution containing 0.250 moles of sodium hydroxide. Okay, let's do that. Remember, molarity is moles per liter. Read your problem. Here is your volume. Here is your moles. What are you going to have to do with the 150 milliliters? Convert it to liters. Molarity is moles per liter. kind of answer do we get there?
One
1.67 molar sodium hydroxide. That is the way the answer should be expressed. Not just what is the molarity of this, but what is it? It's sodium hydroxide. You see, you could have that 1.67 molar of anything. Sodium chloride, copper sulfate, anything. So it's good to say what thing it is. Now, you can see what we did with the 150 milliliters. You divide it by 1,000. Now, dividing by 1,000 is the same as moving the decimal place over 3 places. So you can easily convert milliliters into liters by moving the decimal place over 3 places. So tell me, 350 milliliters equals how many liters? 25 milliliters equals 5 milliliters. Okay? So just move that decimal point over 3 places and you're converting. What you're doing is dividing it by 1,000. And that is the same difference right there. Let's do one more problem. Wait, that's the same one. Is that the same one? Okay, calculate the molarity of a 150 milliliter solution that contains 10 grams of sodium hydroxide. Remember, molarity is moles per liter. That equation guides you as to what has to go in the numerator, what has to go in the denominator. You're in a very dangerous seat, like, you know that? Copper sulfate is not very dangerous. A little bit more sodium chloride. Those of you that are figuring out the molar mass of sodium hydroxide are on the right track. We've got grams here, sodium hydroxide. Okay, and the way I like to set these up is go ahead. You've got a numerator, you got a denominator. You've got something you're given here, 10 grams of sodium hydroxide. But you need that to be moles. So in the numerator there, I'm converting my weight of the solute to moles of the solute. And then in the denominator, I'm putting the volume of the solution. All right, we end up at the same point. It so happens that 10 grams of sodium hydroxide is 0.25 moles of sodium hydroxide. So we end up with the same exact answer as the previous problem. Okay. That should cover molarity. We have to, one other thing we got to do in here is dilution. I showed you an example of diluting a solution. We got to come back and show how to calculate. How would I dilute a solution to a given molarity? The request was made, and I will grant it, to move this module's assignments due Tuesday night at midnight. They're due at Monday. They're due at Monday. I wasn't going to single that person out.
I'll single myself. They all know who to pick.
You all know who to give a Starbucks gift card to. Right?
That is correct.
Okay. I'll try to go do that now, is move those to midnight on Tuesday. And on Tuesday, we'll try to finish this chapter and even start the energy module. When are we supposed to have another test?
I have no idea.
I think it's just the final, that's it. I think so, pretty sure.
Well, I hope it's not Tuesday. There is another test.
Yeah, there's exam
It's the last
3.
day of the class, isn't it?
December 12th?
Let's see.
The final after that?
December 4th.
On the 4th.
That's the next one.
Test 3 and then final.
Okay, we got our work cut out for us next week.
I had that yesterday, and I didn't study for it. I got a 9 I guess I'm pretty smart. I didn't finish my water so stupid. Oh, you got me so mad. Like, I was so close, and I got one question wrong, and it happened all the way back. And he had to shut it over again. And oh my gosh, I almost had a mental breakdown. I couldn't do it.